Okay, use one yourself and pass the rest on. Okay. So guys, again, make yourself your name tents. You have 5 minutes before we start. I'd like to know who you are, and I will be walking up and down the room. I discovered that, oh wait. Apparently this mouse works. So which means I can actually be up back there. Yes. Uh-oh. I lost my skull. Good girl. Go on. I need my sword. Ah. Yes. Oh, they should have been. Karan, the slides are not on the website. Okay. They were supposed to have gone up last night. So, all right. You weren't observing when I made the tent last class, right? You weren't observing when I made the tent in the last class. This is how you do it. Hey. Do I see you in the other class too? No, I don't. It's kind of bizarre that the only people who can see who's online are the people sitting at the back of the class. What's wrong? You get your name tent. Let's take one of those paper sheets and make it. That's beautiful. Oh my. Yes. We should do a little tutorial on how to do that. It's really small. That's okay. I can see it. Eric. Yeah, no, just appreciating the calligraphy. That's beautiful. All right, everybody. Morning, and I'm glad you managed to make it to an 8:35 a.m. class again. what is likely to happen as the days get shorter is that you'll feel less and less motivated to come here. And in the final class in December, the only 4 people in class will be myself and my 3 TAs. So I don't want that to happen. Please be here, right? Unlike past semesters, I'm not going to try to bully you into being in class. I'm trusting your judgment and your common sense and motivation. All right, let's start. We sort of introduced what neural networks were in the last class. We're going to continue on the same topic in today's class and take another deeper look at what they can represent. We will have another class on Friday this week. This is possibly the only week where we'll have a class on Friday. That's because Monday is a holiday, and I have some topics to cover, so I'm going to be using the recitation slot for a lecture. Be here. So the topics for the day, please don't get distracted by that mouse flickering around. It's annoying, but it's useful. So the topics for the day are what can a neural network represent, and what are the restrictions of on the neural network in terms of depth, width, activations, etc. in determining what they can represent and how they can learn to represent it. So here's a quick recap. We've seen that neural networks have taken over all of AI tasks. Things like speech recognition, translation, playing games, just imagining things, captioning images, computer vision, all of these. You name the AI task in the state of the art is being achieved using neural networks. In every case, the neural network is this black box which takes in an input and produces an output. So it's really a function. And we want to know what's inside those functions. All of the tasks that we just saw, we figured are in some sense related to human intelligence. These are things that humans perform. So we would like this function to emulate the human brain. And so if you take a closer look at the human brain and the basic form, we know that the neural networks emulate the networked structure of the human brain because the human brain is basically just a network of neurons. And the individual neurons look something like the figure to the left. A simplified model for it is a unit where you have a number of signals coming in. Each signal coming in has some weight. If the weighted combination of all of the inputs exceeds some threshold, the neuron fires. Otherwise, it stays quiescent. And the brain itself is a network of these units. So our computational models, they basically mimic the structure. They are a network of very simple units. So here's the magic. Each of the individual units is really very simple. All of the complexity of what this thing can perform comes only from the manner in which they are connected, as opposed to the standard mathematical models you might be familiar with, where the model itself is complex, the math is complex. Here it's not. Every single unit is doing something trivial. But just based on how these things are connected, the entire contraption can do some fairly magical things. So the individual unit here we saw was the perceptron, or we called it the perceptron, which is somewhat of a poor take on Rosenblatt's original perceptron. But here's the unit. It has a, can I use this mouse? I'm going to try to use it. Or maybe this. So the perceptron has a number of inputs. Corresponding to each input is a weight. And so it considers the weighted sum of inputs. And if the weighted sum of inputs exceeds a threshold, the perceptron fires, otherwise it does not. A slightly better figure, instead of just saying that I'm comparing a weighted sum of inputs to a threshold, you can say I'm computing an affine function of the inputs. And if this affine function is non-negative or positive, the output is going to be a 1, otherwise it's 0. So you don't have your names, guys. But maybe you can tell me your name and tell me what the difference is between affine and linear. Okay, what's your name again?
Adam.
You're Adam, okay.
The constant term.
The constant term, your name please?
James.
James, thank you. So visually, if I were to plot it, what was the difference between a linear function and a affine function? So a linear function, if you just equate it to 0, this represents a hyperplane that goes through origin. An affine function has something that's shifted. It could be going through any place in the space. So you compute an affine function of the input, which I've represented as z over here. And then you put this affine value z through a function, through an activation, which is a threshold function, which outputs a 1 when the input is non-negative and 0 otherwise. So this is still the same model as this guy over here, right? And once you draw things in this manner, then you can make a few modifications. You can say I compute an affine function of the input, and now instead of putting it through a threshold activation, I can put it through something which is smoother, like the soft perceptron, which uses a smoothed version of the threshold function, which is the sigmoid. The formula for the sigmoid is on the screen. We'll spend some more time looking at what this, at the formula itself, what it means, and the interpretation of the output. But then you could also have other kinds of functions inside that box, like a tan h, or these two functions to the right, the soft plus, or the rectified linear function. Now, these are all things that you will encounter. The point being that once I recast my perceptron as a unit that first computes an affine function of the inputs and then puts it through some kind of activation, then I have greater flexibility. But for now, I'm going to continue assuming that this box has a threshold activation, because that makes it very easy for us to understand some of the things that go on inside the neural network. Here's a poll number 103 on Piazza, please.
Not multi-choice.
Well, it was supposed to be, right, maybe it's poorly set up. But then suppose, why don't you guys answer me, right? Lisa, it's on Piazza. Piazza poll number 103. Piazza post number 103. So is 3x plus 7y a linear function, or is it affine? Is it affine? Because an affine function is also a linear function, right? I mean, linear functions, or rather, linear functions are also affine functions. 3x plus 7y plus 4, is it linear? But it's affine, right? What about 3x plus 7y? Is that an affine function? Because linear functions are also affine, right? And so obviously the fourth one is also an affine function. You get the idea, right? 3 of them are right, the fourth is wrong. Now, we also saw what a multi-layer perceptron was. A multi-layer perceptron is basically a network of these perceptron units where each perceptron's output feeds to other perceptrons. Now, in saying all of this, I am using a magic term. What is it? It's there on the slide. You just have to look. What is the magic term that I haven't introduced yet? The term layer, right? I cannot be speaking about layered networks without talking about what a layer is. We will get to that in a bit. But before that, pretty much all discussion of neural networks these days is about deep neural networks, right? So what is a deep neural network? A deep neural network is a network that is deep. How do you define deep? Anybody know? Number of hidden layers. There's actually a formal definition to it. So this gentleman in the middle, do you mind closing the laptop? Thank you, right? So there's a more formal definition to it. Anybody familiar? So how do you define depth? Thank you. There you go, right? So if I think of any graph, any directed graph, it's going to have a source and a sink. And all paths flow from the source, from a source to a sink. Now, if you consider paths through the network's paths are going to, let me stop this. You'd have multiple paths from the source to the sink here. In this case, you have this guy going up here and down there. It's 2 legs long. But this one, you also have this one, which is just 1 leg long. The longer of the two is 2. So the depth of this graph is 2. On the other hand, if you look at this guy, what is the depth of the graph to the right? 3, right? Because the longest path is 3 long. And so when I'm looking at a neural network is basically, at least most neural networks are directed graphs. You have information flowing from the input to the output. And so the input is the source, the output nodes are the sinks. And if the depth of the network is the length of the longest path from the source, which is the input, to the sink. If this is greater than 2, then you're going to call the network deep. So is the network to the left deep? Okay. What about the one on top? What's the depth of the network on top? Each box represents a layer. 2, right? Is that deep? No, okay. So what about the one at the bottom? Is that deep? And what's the depth? 4, 1, 2, 3, 4, correct? So, fine. Now, how do you define layers? I have a network over here, and this network has some depth. It has a number of layers. Can someone identify all the neurons in the first layer? Which ones would it be? Would they be? Pardon me? The source is not the first layer. The source is the 0th layer, right? Which are the neurons in the first layer?
At depth 1.
Depth 1 from the source. So that would be, that would be these guys, right? 1, 2, 3, 4. What about the neurons in the second layer? Depth 2. So you get the idea, right? Don't get fooled by how I draw the picture. A layer is very formally defined. A layer is the set of all neurons which have the same depth with respect to the input. So consider here, for example, these yellow neurons. The yellow neurons have paths of different lengths coming in. The longest path is 3 long. So the 2 yellow neurons are the 3rd layer. The one in the middle, the green, that's not part of the 3rd layer, right? So the green is part of the 2nd layer. The blue, which connects directly to the green, it's actually the 4th layer. So you have to be careful about designating layers in a network of this kind. Now, a multi-layer perceptron is a network of perceptrons with many layers. And if it's directed, by definition, it's going to have layers. It's just that you'd have to be careful in identifying the layers. The inputs can be Boolean or real stimuli. The outputs can be real or Boolean values. Now, what kind of input-output relationships can this network compute? Just give me a second. I'm going to change my... This thing is getting very distracting. What kinds of input-output relationships can this network compute? That's the topic that we're going to be discussing today. So we've seen that MLPs can compose Boolean functions. They can also can compose real-valued functions. So what are the limitations? We're going to look at each of these. We're going to look at multi-layer perceptrons as universal Boolean functions. We're going to look at them as universal classifiers. And we're going to look at them as universal approximators. which means the ability to approximate pretty much any function that you give it. And in each case, we're going to discuss the issue of depth and width and what makes the most sense. This last bullet is something I will not touch upon in class, but you have these on the slides. So let's consider Boolean functions. How well do MLPs model Boolean functions? We've already seen that a perceptron can model any Boolean gate, right? Just to recall, Nihar, what was the gate to the top left? And, right? And Thomas, what was the one to the top right? Not. And what about the one at the bottom? Nora. What gate was this? That's an OR, right? So you can see that it can model any Boolean gate. And we also saw that a simple but then a perceptron can do a lot more than that. Here is a crazy perceptron. It has weights of 1 with respect to the first L inputs and -1 with respect to the remaining inputs. There are n inputs in all. This net perceptron will fire if and only if the first L inputs are all 1 and the remaining inputs are all 0. Can someone tell me why? Pardon me?
Threshold is L.
Mm-hmm.
So the max value that you can reach through the network is L. So you need all the ones to fire.
Correct. And what happens if any of the ones below become 1?
Then it will be less than L.
Then it's actually going to become less than L, right? Now here is a network, your neuron, that will fire if any of the first L inputs are 1 or if any of the remaining inputs are 0. How does that work? Can you tell me? So here's the simple answer. Flip it, right? What is the only condition under which it will not fire? If all of the first L are 1 or first L are 0 and all of the remaining L are 1. What is the total input at that point? L minus n, n minus L, right? So L minus n plus 1 is the threshold. At that threshold, if any of the first L are 1 or any of the remaining are 0, this is going to fire. So you can see that this is actually a pretty powerful little unit, right? You can also do something, a majority gate. It will fire if at least k of the inputs are 1. And if you set k to be n over 2, then you get a majority. So a simple Boolean gate cannot perform these operations. If you want to have a Boolean network performing majority, it's going to be exponentially sized. But a threshold gate, a single threshold gate can take care of this. So this actually caused people to sort of overestimate the power of threshold gates for the longest time. But then we found that a threshold gate cannot model an XOR, right? So how did we model the XOR?
Using 3 perceptrons.
Using 3 perceptrons. The first one modeled a X and Y. The second one modeled not X and not Y, right? And the third one modeled, and then the third one just OR the 2. So, and so you got the XOR. In fact, you can do this with only 2 neurons. I'm going to wait for a bit. Hold this in mind, right? And at some point later in class, I'm going to ask you why we think we can do an XOR with only 2 perceptrons, okay? But then once we do this, we realize that we can compose arbitrary Boolean functions with the XOR, because with the multi-layer perceptron, you can do every single possible gates. Any Boolean function is composed simply by networking the gates. No big deal, right? So this means MLPs are universal Boolean functions. Again, what do I mean by this statement? It doesn't mean that any MLP is going to compute any Boolean function at all. That's not what it means. What this means is that if you give me a Boolean function, I can always construct an MLP that will compute it. So MLPs are universal Boolean functions in that for any given Boolean function, I can compose an MLP that will compute that Boolean function. So in this example, and this can be over any number of inputs and any number of outputs. So there are no restrictions over here. You can just, after all, it's just a Boolean network, and a perceptron can model a Boolean gate. Now, in the examples that we saw, like the example to the left, I have a multi-layer perceptron, but it has many layers, right? So can we take a guess as to how many, we know that an MLP can model any arbitrary Boolean function, but given a Boolean function, how many layers will the MLP need to model the Boolean function? Can anybody tell me? Yes? Two. Two should be more than enough, right? Explain.
I think that you can make a hash table where you can encode every necessary true value in the first layer, and then the second layer.
Beautiful, right? So here's how it is. What is a Boolean function? A Boolean function is just a truth table, correct? I can explicitly list out every combination of input for which the output is 1. So it doesn't matter how complex the Boolean function is, eventually it's just a truth table. But then, what does that first clause say in the truth table? The first clause says that if x1 is 0, and x2 is 0, and x3 is 1, and x4 is 1, and x5 is 0, the output is 1, which is the equivalent of saying not x1, not x2, x3, x4, and not x5. So I can have one such clause for every single row in the table for which the output is 1. And now, and I just OR the lot, right? And this is going to give me my Boolean function. And the network, I'm going to have one unit for the first clause, one for the second, one for the third, one for the fourth, one for the fifth, one for the sixth. I OR the lot. Here is my Boolean function. So this function is being represented in what's called the disjunctive normal form, which is an OR of ands, right? And I can build a network of this kind because we know that each of these clauses is basically just a very complicated AND, and we know that a perceptron can model an AND. The final output is an OR. We know that the perceptron can model an OR. But then how large will this one hidden layer network get? To answer that question, so basically any truth table can be expressed in this manner. So a one hidden layer MLP is a universal Boolean function. But then what is the largest number of perceptrons required in the single hidden layer for an n input variable function? Now, can anybody take a guess? He's going to have the answer, yes.
2 to the n minus 1.
It's going to be exponential, right? So why is that?
Because there are 2 to the n possible encodings that you can do for each active variable. You can make it more efficient.
Okay, so he has the answer, but he's saying it differently than how I'm going to say it, right? Here's what you can do. How many of you are familiar with a Carnot map? Right. What is a Carnot map, Bobby?
It is a combination which will have the output is 1. So it's like shrinking the which one that you wrote in the previous.
So you're giving me how to compress it, but what is the map itself? Can anybody tell me? It's actually a topological representation of a truth table, right? So you see this two-dimensional plane. Every column, the 4 columns represent the different combinations of YZ. The 4 rows represent the different combinations of WX. And if you look at any 2 adjacent columns, they differ in only 1 bit. So which means that the rightmost column also is connected to the leftmost column. It's actually a cylinder. If you look at any 2 rows, they also differ in only 1 bit. So the topmost row is connected to the bottommost row. The whole thing is actually a toroid. And now, this is a topologically accurate way of representing all 16 combinations of my 4 variables. Any 2 adjacent boxes differ in just 1 bit. I can represent my truth table by just highlighting the specific boxes for which the output is 1. In this case, there are 7 combinations for which the output is 1. So my basic DNF formula is going to require 7 units, or 7 terms. And so a very trivial MLP that I compose is going to have 7 hidden neurons in the first hidden layer and the output, final output neuron. But then here's something I can do. I can begin grouping things up. If you look at the first column, all 4 entries in the first column are highlighted. What this tells me is that it doesn't matter what W and X are, so long as Y and Z are 0, 0, the output is 1, right? Similarly, I can group the two elements in green, which tells me so that it doesn't matter what Z is, regardless of whether Z is 0 or 1, it will fire so long as Wx is 0, 1 and Y is 0, right? And so also I can group the four corners. And so each of those is now going to give me one clause. The first vertical column just says not Y, not Z, which says Y and Z are going to be 0. So I can group things up, adjacent things up. I get a much reduced DNF formula, and the one hidden layer network that I require for this is simply going to need one perceptron per clause. What arrangement of ones and zeros simply cannot be reduced? Chessboard, right? Checkerboard. So something like this doesn't let me group anything. In this case, how many clauses will I have in my DNF formula? 8 over here, or more generally, 2 raised to n minus 1, right? So how many neurons will I need in my hidden layer? 2 raised to n minus 1, right? So, or here is our version where I have 6 variables. I've created a 3-dimensional Carnot map. And once again, you can see that over here. This is a Boolean function of 6 variables. And if I want to have only one hidden layer, I cannot use fewer than 32 neurons, 32 units in the hidden layer. So in general, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer. This is exponential in n. As the number of inputs increases, the size of my network, the width of the hidden layer is going to increase exponentially. Can I make it smaller? What happens if I make it deep? Does anybody recognize this pattern? What is this? It's an XOR, correct? So first, here's a poll. All right, I'm going to stop it at 30 seconds. Can anybody tell me the answer? Okay, someone on Zoom, tell me the answer. What is the answer? Thank you, Meghna. The answer is 512, right? Perfect. So how many units will we require if we use multiple hidden layers? Oh my, now we're going to get clobbered. So how many units will I require if I use multiple hidden layers over here for this problem? Does anybody want to guess? So here's how it is, right? The first one is the XOR of W, X, Y, and Z. The second one is the XOR of 6 variables. How many perceptrons do I require for an XOR? That's my XOR. So I'm drawing the three perceptron variant of it. And so that first guy is going to be W XORed with Y, X. The result is XORed with Y, and that result is XORed with Z. 9 perceptrons. If I use 2 perceptrons for an XOR, then I'm only going to require how many? Shreya? If I use 2 perceptrons for an XOR, how many perceptrons will I require here? 9. With 2 for an XOR?
We have 2 for XOR, but like if we are doing it by like tagging.
So, Ishani, can you tell me? You're going to need 6, right? There are 3 XORs. Correct. So much smaller. What about this guy? I have 5 XORs, right? I'm going to need either 15 or 10 perceptrons. So once I begin making my network deep, the number of perceptrons is going to decrease dramatically. More generally, the XOR of n variables is going to require either 3 or 2 times n minus 1 perceptrons, correct? So a single hidden layer network is going to require 2 raised to n minus 1 plus 1. What's the final plus 1 for? The final OR, right? So it's going to require an exponential number, an exponential and n number of perceptrons, whereas if I let it go deep, it's only going to be linear in n. So you see how depth changes the number of perceptrons you will require to model this function, right? Dramatically. But then, how deep must the network be? To see how deep the network must be, let's sort of reorganize this network. Now, an XOR is associative, correct? What do I mean by that?
If you change the location like X or Y XOR X would be the same value. Like it is.
Is that? No, that's commutative, right? What does associativity mean? You can group things in any which way, correct? So now I can group that sequence of XORs as X1 XOR X2. That output is XORed with the XOR of X3 and X4 and so on, right? So in our network, what this means is that I can pair things up like so. The first 2 units are XORed. These 3 neurons are going to give me the XOR of the first 2 inputs. Then I XOR the next 2 inputs, then I XOR the next 2 inputs, and so on. I have a bunch of variables. Now those things can be XORed pairwise, and I keep going down all the way down the tree till I finally end up with 1 output. How many layers will this structure require? Anyone? If I have n inputs? Do I have to pick a name, or is someone going to give me an answer? So Peter, how many layers will this require? I have n inputs. I'm grouping them in pairs. It's going to be log of n, right? And each XOR needs 2 layers. So it's going to be 2 times log of n, right? But then here is the crazy thing. If you look at it, each of these gray boxes is going to compute a bunch of values, and downstream, what you're performing is an XOR of the output of the variables that are coming out of the gray boxes. So if I decided that over here, this particular network is going to only have 4 layers, then what is the width of the layers going to be in the best case? If I decide to have only 4 layers, after 2 layers, I've halved the number of variables, correct? But then from there, I still have an XOR, and I have only 1 more hidden layer. That's going to have to be exponentially sized, right? And so anytime you have a fixed depth network, it has to be exponentially sized to capture everything. So suppose I decide to have only 4 layers over here, right? In the best case, I can use the first 2 layers to compute a bunch of pairwise XORs of all the variables. But then downstream, I'm XORing those variables themselves, right? So I'm XORing n over 2 variables, but I have only 1 more hidden layer. It's going to be exponential, right? So what this means is that a network with a fixed depth is likely to end up being exponentially sized to compute this function. If the depth of the network is proportional or to the number of inputs, then the network can be much smaller. So again, the actual number of parameters in a network is not the number of neurons, it's the number of connections. Here there are 30. This is the number that actually matters in software or hardware, but again, networks that require an exponential number of neurons are going to require an exponential number of bits. So we have, it hasn't made the problem better or worse. So what we find is that deep Boolean MLPs that scale linearly with the number of inputs can become exponentially sized if you have only 1 hidden layer, or if you just fix the number of hidden layers. If you limit the number of hidden layers, then beyond a point, the network is going to need to be exponentially sized, right? So the summary is an MLP is a universal Boolean function, but it can represent a given function only if it's sufficiently wide, because it has to capture all the classes. Yes, Nate?
So
we talked earlier about how the number of perceptrons isn't necessarily what's important, it's the number of connections.
Correct.
The connections contain the information. It seems that the deep network allows for a greater density of connections. Like for instance, the same XOR function with a deep network, does that actually contain the same number of connections as the single layer?
So think about this. Even if every neuron is connected to every neuron, right? If the size of the network is, the number of neurons is linear in the input, you're only going to get a polynomial number of connections.
Okay.
So it's going to end up being polynomial if it's deep, exponential if it's not.
Okay.
Does that answer your question?
Yes, sir.
Okay. So an MLP can represent a function only if it's sufficiently wide, or only if it's sufficiently deep. Depth can be traded off for sometimes exponential growth of the width of the network, and the complexity. So optimal width and depth depend on the number of variables and the complexity of the Boolean function. To answer the question on Zoom, the catch, in a practical implementation, you're always going to have finite depth. We're going to have other issues like trying to train the network and so on, which becomes really, really hard as the network becomes arbitrarily deep. And very often your inputs don't have a fixed size. For example, if you're working with recurrent inputs or images, which can change in size. So in that case, there's a notion of trying to have a network whose depth varies with the size of the input becomes challenging. Your practical implementation is always going to have fixed depth. So you have all of these problems. So the story so far, MLPs are universal Boolean machines. They can compute any Boolean function. Even a network with a single hidden layer is a universal Boolean machine. We saw that. But a single hidden layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same Boolean function. They can be exponentially smaller. So that's with Boolean functions, right? But then the next thing, if you take one step further, you accept real inputs, you produce categorical or Boolean outputs. That's a classifier. We also saw that MLP is a universal classifier. Now, we saw that in the case of classification, working on real inputs, the MLP is a function over real inputs, and it finds a complex decision boundary over the space of reals. Now, here's what we saw the perceptron to be. It's computing an affine function of the inputs. If that's non-negative, the output is 1. Otherwise, the output is 0. Alternately stated, if the weighted sum of inputs matches or exceeds a threshold, the output is 1. Otherwise, the output is 0. So now the perceptron is a step function, right? If I have a Heaviside step function. And we saw why a perceptron can now model Boolean gates. What was the top left again? Top left gate again? Or the one in the middle? Not. And the one to the right? What is the one to the right? Someone, guys, somebody give me the correct answer. We just got 100 wrong answers. XOR, right? Can a perceptron model that? No. Okay, now. So how did we solve that problem? The way we solved the problem was that we had these 4 possible inputs, and we had one perceptron for this boundary, correct? With the one going in this direction, the other perceptron for this boundary with the one going in this direction, and then we ORed the 2. That's how we got the 3-unit perceptron. Can someone tell me how I can do this with just 2 perceptrons?
Just a guess, is that a 2 NOT gate?
Pardon me?
Is that a 2 NOT gate?
No, you can't do this with Boolean gates, right? Can someone tell me how? Just look at the figure and tell me.
We can have 1 over there and then minus 1 over.
Somebody, just in terms of the picture, can you tell me?
We can have one perceptron and the second one will just threshold it to 1.
So here is what I can do, right? This is where you have to begin thinking differently. I have these 2 lines. I can have my first perceptron capture this line, one to the side, And the second perceptron is a combination of 3 inputs, which is it has to be to the right of this guy and the left of this guy. And so I capture I can actually get, so think it's to the left of this and the right of this. That's just a simple AND, correct? And so, and that's how you got the 2-unit perceptron, 2-unit XOR. Anyway, here's a poll. This one. This second guy is saying A, not A or not B. Actually, it's, if I think of it this way, it's A and B and C. Right? So it's a negation, or rather, it's not A and not B and C. So where C is to the right of this guy. Yep.
Can you explain again why the second perceptron needs 3 inputs, like in the diagram that you drew?
So in my example? Okay. So she's asking how I can explain this. Think about this. This perceptron is going to say not 1, 1 and 1. So I'm saying it's going to be the left of this and to the right of this. Did that answer your question? I guess not. So look at it this way, right? This perceptron is going to tell you that the input is in this portion of the space, correct?
Yeah.
Now for this one, if I want to capture this band, I want it to be in this space, right? So the output over here has to have a weight 1. But I want it to exclude this. So the outputs, I think the weights would be -1.
Okay.
Right? So that's how you got it. Anyway, I'll stop here. We've gone way past the 2-minute mark. Can anybody answer this question? Somebody on Zoom, answer this question. The guys on Zoom. Okay, someone here, answer the question. Zoom. It's true, right? Okay. Thank you. All right, we also saw how MLPs can model complicated decision boundaries like this pentagon. And all we need to do is to have one perceptron for every one of these lines, and then you OR the lot, right? But then once you do this, okay, the decision boundary here is this pentagon, right? But if my final OR had a threshold of 4, what is the decision boundary going to look like? It's going to look like a star. So it doesn't mean that you can only get convex decision boundaries. You can get arbitrary decision boundaries, even with the simple model. First point, right? But then once you do this, you know how you can, I'm sorry, did I damage your, no. Okay. So once you do this, you can see how you can construct more complex decision boundaries like the double pentagon or these things, right? All you'd have to do is to partition it into many little polytopes, compose one subnet for every one of these guys, and then OR the lot. But then, in these cases, I've needed at least 2 hidden layers, right? Can I do this with only 1 hidden layer? So here's my question. We already know that a 1 hidden layer perceptron, a multi-layer perceptron, can model non-convex decision boundaries, correct? How about this? Can I get a 1 hidden layer MLP that gets me this double pentagon? Anybody? If someone has to take a guess, then let me ask, sorry. Let me ask Nathan there, who's thinking hard, how you would do this.
I have no clue actually.
Okay, you don't have a clue. That's along with the rest of the class, so you don't have to be embarrassed about it, right? It took me a long time to figure it out myself. But anyone else? Arjun? Someone? Zora, can you take a guess? Yeah.
I guess it's yes.
What is yes? How would you do it is my question. Overfit. So here is the thing, right? I can't just come up with some lines and combine those things because, for instance, if I try to model each of those 10 lines and then try to come up with some logic, I'm going to also end up capturing the region between the two pentagons. I will not actually get the double pentagon decision boundary. Yes?
So I mean, the problem is the two figures require and kind of combination, and then we have to OR it. So instead of doing that, if we take the opposite side,
It won't make it.
excluding the
You're still going to end up with the same issue. So here's what you have to, here's how you want to think about it. Let's say I want to have just this diamond-shaped decision boundary. Then I can just have 4 neurons, and the sum of their outputs is 4 inside the diamond and 3 outside. If I use a threshold of 3, I'm going to get all the yellow regions as well, which are infinite in size. A threshold of 4 is going to give me the diamond, right? If I have a pentagon, I need 5 perceptrons, and that's going to give me a 5 inside the pentagon. But the area where the sum is 4 is not infinite anymore, it's finite. If I do a hexagon, again, this figure is actually showing the sum against the inputs, right? So you can see that it's 6 inside, and the region where the sum is 5 or 4 is much lesser. I can keep increasing the number of sides, right? What do you think is going to be in the limit? This figure, this sum figure, what's it going to look like? Circle? No, it's not. It's a 3-dimensional figure, right? It's a a cylinder, kind of a cylinder, right? I know you meant cylinder, but you were telling me, okay. So here's what you get with 16 sides, with 64 sides, with 1,000 sides. Is it looking like a cylinder? So the actual formula looks like so, this ugly thing, which was worked out for me by one of my deep learning students many semesters ago. So I didn't work it out. I'm not capable of that math, but CMU students can. The sum is n inside the circle, and then rapidly falls off to n/2 outside. So roughly speaking, I can say that it looks like so. It's a cylinder with n inside and n/2 outside. And if I add an extra bias term, which subtracts the n/2, then this is going to be n/2 inside and 0 outside, right? I need the 0 outside. So now what happens? Suppose I have 2 subnets, each of them which has a very large number of a polygon of effectively infinite sides, and then I sum their 2 outputs. This first subnet is going to compose this first cylinder, right? This second subnet is going to compose this second cylinder. What will the sum of their outputs be? It's just going to be 2 disconnected cylinders because one cylinder doesn't interfere with the other. It became 0 outside, correct? Now if I use an OR at the output with a threshold of n/2, what will the output, what is the decision boundary going to look like? It's like slicing it at height n/2, right? The decision boundary is going to look like 2 circles, 2 disconnected circles, right? Make sense? And so now, if I want to compose this guy, here's how I would compose it. I'm going to fill it up with a very large number of circles. It's not a, is it accurate? Or is it an approximation? How precise is it? I can make it arbitrarily precise, right? I can just make each of these circles smaller and smaller, and I can get arbitrary precision. So a multi-layer perceptron is a universal classifier. Even a 1 hidden layer MLP can model any classification boundary, not exactly, but to arbitrary precision. These two are not the same. And this figure will explain why the two are not the same, right? So, but then if I did the same thing over here with a deeper network, I just needed 12 neurons in the first case and infinite neurons in the second case. So again, you can see why depth matters, right? So how deep must it be? Must it be? So we're going to, let me look at a different pattern, worst case decision boundaries. Again, I'm going to be considering threshold activations. Let's consider this 2-input network, which has to construct this, this checkerboard pattern. I want the output to be 1 inside the highlighted yellow regions. I want it to be 0 in the gray regions. Now, this entire network, it's possible to do this with a linear number of neurons, but if I were to do this naively using the technique we just saw, I'm going to end up using essentially infinite neurons if I want to do this with one hidden layer, right? What happens if I do this with 2 hidden layers? I can do this with 56 hidden neurons. Why so? That's because the checkerboard is composed of 16 lines. And so I'm going to need 1 neuron in the first hidden layer to capture each of these lines, right? And thank you. We need some drama in class. And then what about the second layer? The second layer is going to have 1 perceptron for every one of these little highlighted regions. And so there are 40 of those regions in all. So the second layer is going to require 40 hidden neurons, a total of 56 neurons, right? 57 including the output neuron. But then this is just, once I capture the lines, this is just an XOR, right? Checkerboards, they're XORs. And the XOR is going to require 16 neurons for the first layer. And then subsequently, there are only 15 XORs. Each of them requires 2 neurons. 30, I can do the whole thing with 46 neurons, right? Now, if the difference between 56 and 46 doesn't appear to be very large, think of something more complex like this. And this is actually a very trivial pattern in the real world. This is a grid formed of 64 lines. I want one in all the yellow regions. I'm going to need the first layer of 64 neurons, 1 for each of these lines. And then if I were to do this with 2 hidden layers, I'm going to need 1 neuron for each one of those 544 yellow regions. And so a total of 609 neurons, including the output neuron. But then if I were to do this using the XOR, this is only going to require 190 neurons. So as you can see that, increasing the depth, even in these examples, can reduce the number of neurons required exponentially. You're looking at 2-dimensional patterns over here. If you go up to a 1,000-dimensional pattern, then the difference can be enormous. And 1,000 dimensions is really minuscule in the real world. So the point is, the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input. This is the worst case. Or alternately speaking, it can be exponential in the number of statistically independent features. Now, let me go back a few slides over here. And let's go back to my XOR pattern. What happens if I have 1 neuron less in this case than the minimum required? What will the output be? How wrong is it going to be? Can anyone tell me? Just 1 neuron less. So here's the magical thing about XORs. If you miss 1 bit, the error becomes 50%. You're going to be wrong half the time, right? That's how sensitive it is. Think about it. In an XOR, if you can just think about the pattern, you eliminate just 1 bit, they're going to be wrong in half the space, right? So it's going to be, it's very sensitive. As you get closer to the minimal number of neurons that you need for the function, it ends up becoming increasingly sensitive to going below the critical number of neurons. Where were we? So the story so far, just the bit that we added is the bit in red, where we said that deeper networks may require far fewer neurons than shallow networks to express the same function, and they could be exponentially smaller, which means that deeper networks are what we will call more expressive. They can express a larger class of functions, right? Finally, as universal approximators, everything that we've seen so far had Boolean or categorical outputs. But what if we want real valued outputs? We've seen this for the one-dimensional case already in the last class. If the input is scalar and the output is scalar, then I can compose a little network with just 2 hidden neurons, which produces a 1 in the between the two thresholds and 0 elsewhere. And then I can take my one-dimensional function and approximate it with by just filling it up with several of these little pulses, right? So here, I assume you agree with me that a one-dimensional function can be approximated to arbitrary precision using a neural network. You're sitting way out in the corner. Do you want to come up here?
Sure, I have the Zoom open so I can hear you all the time.
You're better off up front. Just come on, right? Why do you want to hide in a corner and find yourself in the most uncomfortable spot in the? You can. I think there's a chair up front, or you can sit at my table.
All right.
Right. Okay. Shreya's giving me a chair. Perfect. Yes. There you go. Thank you. I wasn't bullying you. I just found you sitting in the really bad spot.
More comfortable, I would say.
I need your name tag. I need to know who you are, right? But now if I have higher dimensions, how am I going to solve the same problem? Can somebody tell me? Here we saw how we could do this, right? If I had a 3-dimensional function, or even a function in 2 dimensions, how would I do the same approximation? Yes? What are the building blocks? Lovely, right? Sabrina? Lovely. Yes, so here's what you'd have to do. You can't do it with squares. You can't do it with cubes. You will have to wish you need coffee. Just go out and wash your face. So here's how we're actually going to be doing this. You'll be filling up the space with cylinders, scaling them up, and then you can approximate any function. Again, is this precise or is it an approximation? It's an approximation to arbitrary precision. Yes? Yeah. Pardon me? Not at all, right? You're just going to need an arbitrarily large number of them. That's it. So here's a poem. And believe it or not, we've just gone through 131 slides. I don't know if you noticed, but we just did. Okay, I'm going to stop this. Someone on Zoom, give me the answer. I'm guessing Meghna is going to give me an answer again. Yeah, there, obviously, right? A whole lot of them, yes. I see some trues and some falses. It's false. It can only be approximated, right? It cannot be captured. There is no guarantee that you will get the function precisely. Now, final topic for the day. We have 15 minutes left. We're going to discuss the issue 20 actually. Issue of sufficient depth and width. By the way, any questions so far? Any questions? Yeah.
Yeah, in the whole fourth question, you did say that there's an infinite number of neurons, right?
It doesn't matter. Infinite is just going to keep making the error smaller and smaller. You can approach 0. You're never going to go to 0.
Infinite is, although a different concept from arbitrarily many, right? We're talking about arbitrarily.
Even with infinite, it's discrete, right? These are all discrete entries. You're really looking at the difference between different infinities, the reals versus integers. Yes. Right, it has to be countably infinite. Each cylinder is a discrete entity, right? You cannot fill it up. So, thank you, Yu Cheng. You're absolutely right. So, the previous discussion showed that a single hidden layer MLP is a universal function approximator, can approximate any function to arbitrary precision, but may require infinite neurons in the layer. More generally, deeper networks will require far fewer neurons for the same approximation error. We've already seen this, right? But there are limitations. For that, let's go back to this network. Again, if I'm using threshold activation neurons, right, what is the limitation over here? A neural network can represent any function provided it has sufficient capacity, which means it's sufficiently broad and sufficiently deep, and not all architectures can represent any arbitrary function. So here we needed 16 neurons in the first layer and 40 in the second. If I'm using threshold activations and if I have only 8 neurons in the first layer, but I allow you to have any number of neurons in the second layer, I allow you to have 5 million layers, I don't care. Can I still get this decision boundary? Yes or no? You're saying no, why not? The answer is right, but why not?
You need more lines. You can't model this.
Thank you, right? So my 8 decision neurons in the first layer may perhaps get me these 8 lines, correct? With these 8 lines, all you can say, because the activation is a threshold activation, the output is either a 0 or a 1. It's going to tell me in which of these 8 regions the input lies. This is the information being passed downstream. Is this sufficient to reconstruct the rest of the hash? No, okay. Even if my 8 neurons captured these boundaries, are these enough to capture the rest of the hash? Again, no, right? So this is, these lines can only tell you where in the 25 cells you are, but it can't tell you exactly in which cell you are, but not where you are in the cell. Yes.
So when you think about, as we are trying to minimize the number of lines that we want to have to represent a network. So if we, so do we have a, like, okay, I am okay with this much error or something like that, if it was a large network?
Yeah, I mean, you're sort of going, you're going way beyond what we are talking about in the class. Yes, you're speaking of trade-offs and such like. But yes, it's a problem like XOR. There's no such thing as I'm going to make 0.1 error. It's either 50% or no error, right? So you have to be careful when you think about these things. Now, similar restrictions apply to higher layers as well. Regardless of depth, every layer has to be wide enough to convey the information downstream so that subsequent layers can construct the pattern that you want to construct. Now, why do we have this problem? The problem has to do with our choice of activation. We were looking at threshold activations, right? So if I have a threshold activation, it's 0 to one side of the decision boundary and 1 to the other side of the decision boundary, which means that if I have only 4 neurons in the first layer, the 4 neurons might maybe capture these 4 lines. And then once you get past the first layer, the only information you have tells you in which of these 5 regions your input is, but it doesn't place you within the region. Correct? So how can you remedy this? Change the activation to what? These are nonlinear. Yes. Yeah, you're drawing the picture on the. So here's what you want. You really need to know how far away you are from the line. If you have that information, then you have enough information to draw more lines. Correct? And so in this case, if I had something like a threshold activation says I'm to the right of the boundary, I'm to the left of the boundary, it doesn't tell you anything more. What you would really like to know is how far you are from the boundary. So if you have something like a smoother version of the threshold, which is the sigmoid, then the sigmoid has this function over here. It goes to 0 when the input is negative infinity. It becomes 1 when the input is positive infinity. And in between, it sort of transitions slowly. At any point, if you look at the output of the sigmoid, it gives you some idea of how far you are from the boundary, right? So now, when you look at the output of these neurons, you actually have some idea of how far you are from the boundary. That information could potentially be used to draw more lines, to draw more boundaries, right? Now, a sigmoid is not really a very good activation in this case. Why is that? By the time you go here, the thing is saturated. So it tells you how far you are from the boundary for a small, for a small distance. Beyond that, it saturates. What would be a better? A tan H is also going to have the same thing, right? Yes.
Something like just a linear one, or a rectified linear.
Rectified linear, right? A rectified linear is going to continue to give you information as you go further and further from the boundary. So why can't I just have a straight line? There is no boundary, right? You need to have something happening at some point. The nonlinearity is critical in that unit. Otherwise, you can give me 1,000,000 linear units and I can compose them all. I end up with another linear units. You're never going to have more than one linear unit. If you want a network which is effectively actually a network, you need these activations, nonlinearities. So something like this will continue to tell you how far you are from the boundary all the way to infinity, right? But unfortunately, it does that only on one side. So maybe something like this guy here continues to tell you how far away you are from the boundary for a very long distance on both sides. And so you continue to have information on both sides of the boundary. In any case, the point is that this simple threshold activation that we are looking at is not really, doesn't carry information about the distance from the boundary. So you really need these other activations which carry information about the distance from the boundary. And the more effectively they carry that information on either side, the better you're going to be. But even assuming that I actually have these activations which carry information about the distance from the boundary, is that sufficient? So here you're depending on luck. If my 4 neurons are capturing these 4 boundaries, it doesn't matter how much information I have about how far I am from the boundary. The newer boundaries I'm going to draw are only going to be parallel to these. They cannot capture patterns that are orthogonal to it. So this is only a partial remedy to having more compressed architectures. It's not a full remedy, right? But these activations actually are going to be essential, but potentially not sufficient. And so the width versus activations versus depth, narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but will require greater depth to permit later layers to capture relevant patterns. Right? And even so, you're sort of dependent on the neurons capturing the appropriate subspaces as appropriate orientations, because you might just lose some information that you can never recover. And so the lesson so far, MLPs are universal function approximators. They can model any Boolean function, classification function, or regression. Deeper MLPs can achieve the same precision with far fewer neurons, but must still have sufficient capacity. The activations must pass information through, and each layer must still be sufficiently wide to convey all relevant information, right? You need to be able to capture relevant information across every direction of relevance. If there's no variation across some dimensions, you don't need those, but you need to capture every possible dimension, right? So there's a final fifth pole. Okay. Let's stop this here. Does anybody want to tell me the answer from Zoom? Answers, anyone? Nobody on Zoom? Ah, yes. And 4. All the usual suspects. Okay. Over here, what do you guys think? 2 and 4. So networks with graded activation functions are more able to compensate for insufficient width through depth than those with threshold or saturating functions. And for a given accuracy of modeling a function, which is to go back to the other question that was asked, networks with more graded activations will generally be smaller than those with less graded, that is saturating or thresholding activations. All of this that we are talking about today speaks about the ability of networks to model functions. It doesn't mean that we know how to actually construct the network to model the function. That's something that we have to deal with through the rest of the semester. What we've seen so far is that the network, if properly constructed with the proper activations, can model pretty much anything you want to the level of precision you want to. So we often like to talk about networks in terms of their capacity to model functions. And the capacity has various definitions, like information or storage capacity, how many patterns it can remember. We like the learning theory guys like to think about it in terms of VC dimension, but it's a particularly useless way of quantifying network capacity. The thing is, a network with insufficient capacity cannot exactly model a function that requires a greater minimal number of convex hulls than the capacity of the network, but it can approximate it with error. So lots and lots of definitions of network capacity. The one I like is the one by Gerald Friedland and Krell, who like to think of it in information theoretic terms. If time permits, or if the class is sufficiently motivated, I may ask Gerald to do a guest lecture sometime later this semester. So the lessons today: MLPs are universal Boolean functions. MLPs are universal classifiers. MLPs are universal function approximators. A single, not single layer, but a single hidden layer MLP can approximate anything to arbitrary precision, but it could be exponentially or even infinitely wide in its hidden layer. Deeper MLPs can achieve the same precision with far fewer neurons. So that means deeper networks are more expressive, and more graded activation functions result in more expressive networks. So that's the last thing for today. 164 slides. I'm shocked at myself. Yeah. computation, among other things, and learning. Right? We have a few minutes. I'll take any questions. In the next class, we're going to talk about, we've seen how MLPs can emulate any function. We'll begin discussing how to make them emulate a function of choice. Yes.
Where an XOR network needs 2 hidden neurons and 1 output neuron. But didn't you draw an XOR network